Okay, so the next thing I want to talk about in this section is sort of a way of expanding on that last theorem that we talked about. So the only theorem actually that we've covered in this section so far says that if T is a linear transformation mapping V into W, then T is one-to-one if and only if the kernel of T is the set containing the zero vector of W. We proved that, but if we add one extra little assumption into the statement of that theorem, we actually get another equivalence, another fact for free. So what this theorem says is that if V and W are finite dimensional vector spaces with the same dimension, this is the new assumption. We're assuming that they have the same dimension. And if if T, which maps V into W, is a linear transformation, then all of the following statements are equivalent. T is one-to-one, the kernel of T equals the set containing the zero vector, and T is onto. Now, in the last theorem, we already proved that A is equivalent to B under the assumption that T is a linear transformation. What we want to do now is tie C into this. And one way to do that is to prove that B is equivalent to C. We want to show that it's technically two directions, if B then C, if C then B, but we can actually do this in the form of one of those if and only if proofs where we handle both directions at the same time. We've seen this once or twice so far. So, how do we do this? Well, we know from the definition of what a kernel is, the kernel of T is equal to the set containing the zero vector if and only if the nullity of T is zero. Why is that? Well, remember, we defined rank and nullity in the previous section in the context of vector spaces and linear transformations. A linear transformation has a nullity of n if the dimension of its kernel is n. We established when we first talked about dimension back in chapter 4 that as a matter of definition, the trivial subspace or the trivial vector space or the zero vector space, as we also called it, has a dimension of 0. The vector space that only contains the zero vector, by definition, has a dimension of 0. So therefore, if the kernel of T is the zero subspace, then the nullity of T is equal to 0. That's what the nullity is. Okay? Now, we established in the dimension theorem in the last section that the dimension of V, our domain in our for our linear transformation, is equal to the rank of T plus the nullity of T. Or, solving for rank, the rank of T is equal to the dimension of V minus the nullity of T. But because the kernel being equal to the set containing the zero vector implies that the nullity of T is 0, then this would just mean that the rank of T is equal to the dimension of V. Okay? However, we assumed at the beginning that the dimension of V is the same as the dimension of W. So now, another way of saying this is that the rank of T equals the dimension of W. Well, what is the rank of T? Remember, the rank of T is the dimension of the range of our linear transformation. And the range is a subspace of W. So this implies that the subspace range of T of W has the same dimension of W. Well, another thing that we showed back in chapter 4, that if a subspace of a vector space has the same dimension as the vector space that it belongs to, then that subspace is the entire vector space. Or in other words, there are no proper subspaces. What I mean by proper subspace is a subspace that as a subset is technically smaller than the set it belongs to, in the sense that it doesn't contain everything that the parent set has. There are no subspaces of finite vector spaces that have the same dimension as the vector space they belong to. The dimension should always be smaller. So again, this assumption that the dimension of our range is equal to the dimension of the codomain implies that the range is the codomain. But we said that that's another way of characterizing the definition of onto. So that would be true if and only if our linear transformation T mapped V onto W. Now that completes the proof because this is stated as a sequence of if and only if steps. It's handling both directions at the same time. Okay? That's incredibly useful because as we've seen, to prove that something is one-to-one and onto is technically two separate proofs. You're talking about two different characteristics or properties that a linear transformation can have. But if you are dealing with two vector spaces that have the same dimension, simply establishing that the kernel of your linear transformation is the 0 vector, you get both of these automatically in that case. And we've done a couple of examples where we did this, and it wasn't really that hard to do. So, before moving on to inverse transformations and more examples, we have another really important theorem to get under our belts. And this is kind of just reusing some results that we've already talked about back in chapter 4, but in the context of linear transformations. So if T sub A is a matrix transformation specifically from Rn to Rm, and remember what this does is it takes vectors from Rn, multiplies them to the matrix A, which is a matrix that you would have defined. It's a specific matrix that you would have chosen for this transformation, an m by n matrix, and then after that multiplication, you get a vector in Rm. So if this is a matrix transformation, then TA is 1-to-1 if and only if the columns of A are linearly independent. And TA is onto if and only if the columns of A span Rm. Okay, so why is that? Well, really, it's just using properties that we already know from chapter 4. So again, let's suppose for a second that TA is 1-to-1, right? Now, we showed in the last section that for matrix transformation specifically, the kernel of a matrix transformation is the same thing as the null space of the matrix A that's being used for this transformation. They mean the same thing. So the kernel of T is the null space of A. But if T of A is 1-to-1, then that implies that the kernel of T has dimension 0 because it's equal to the 0 subspace, which would mean that the null space of the matrix A has dimension 0 as well, which we call that dimension the nullity of A. This is the nullity of a matrix, not the nullity of a linear transformation. So back in chapter 4, we had a version of the dimension theorem for matrices, which says that the nullity of a matrix plus the rank of that matrix must equal the number of columns in that matrix. Well, A is an m by n matrix, and if the nullity is 0, that means the rank must equal m. M plus 0 equals m columns. But if the rank of A is m, one thing that we also showed back in chapter 4, that if the rank of a matrix is equal to the number of columns in that matrix, then the columns of A form a basis for Rm, where again m is the number of columns. If it forms a basis, then as is the case for any basis, the columns must be linearly independent. That establishes that result. Okay, so it's using a bunch of the work that we did in chapter 4. Similar here, so let's suppose T of A is onto. Well, again, remember, how do you prove that something is onto? You pick an arbitrary vector in your codomain and show that we can find a vector in the domain that maps to that vector. So if it's onto, then another way of stating that in the context of matrix transformations is that AX equals B always has a solution for every B in Rm. That means we can always find an X in Rn that has B as an image. But one thing that we showed again in chapter 4 when we talked about row space, column space, is that if this is true, if this matrix equation, remember this represents a system of linear equations, if this is true, then B has to belong to the column space of A. That's what that would mean. But remember, the column space is the span of the columns of the matrix A. So another way of saying that is that the column space of A spans Rm, since every vector in Rm can be written as a linear combination of those column vectors. So that establishes this result. Let's go ahead and move on to the topic of inverse linear transformations now. These are very, very important, and we're going to use this idea in 8.3 when we talk about isomorphisms as well. So let's let T be a linear transformation mapping V into W. And let's suppose that it's not just any linear transformation, but that it's 1-to-1 also. If the linear transformation is 1-to-1, then there's going to exist a linear transformation that we're going to call the inverse of T. and this is familiar notation, right? Because you've dealt with inverse functions since algebra. It's the same thing, same idea here. This linear transformation T inverse is going to map the range of T into V. It's important that we say range of T instead of W, because remember, what an inverse function is supposed to do is if you have a function that maps inputs in your domain into outputs in your range, the inverse function should reverse that. It should grab the outputs from your range, use them as inputs, and send them back to the original inputs that were in V, right? So it's swapping inputs for outputs, basically. But remember, for just any one-to-one linear transformation, W is not necessarily equal to its own range. So there might be vectors in W that never show up as outputs in this function in the first place, which means we can't use them in the inverse function. We can only use those that show up in the range of T. All right? So a way of defining linear transformations is using composition. In other words, for every V in V and for every W in the range of T, if T inverse is the true inverse of this linear transformation T, then if you compose T inverse of T of V, you should get back to V. In other words, T inverse and T essentially cancel each other out and give us the input that we started with. If I do the composition the other way around, I'm swapping the T for a W, because again, T inverse of W has to be plugged into T, which should take me to a vector that lives in W. But again, it's like these two things cancel each other out. So that's how we define the inverse of something, the inverse of a linear transformation. Okay, so in this example, we want to show that the linear transformation T that maps R2 into R3, given this way. So we take ordered pairs of the form x, y and map them to an ordered triple x, y, and then the third component is x minus y. We want to show that this is one-to-one, and then we want to find T inverse. Now notice, we don't care if this linear transformation is onto. In fact, it can't be onto. We'll show that with a different argument later, but as long as it's one-to-one, we can find an inverse function for it. So let's begin by showing that. Remember, in order to show that, we can either use the definition of one-to-one, which hasn't been our preferred method so far, or we can show that the kernel of this transformation is just the set containing the zero vector. So let's do that. So let xy be a vector in R2 such that T of xy equals the zero vector in R3. Okay? Well, from the definition of this linear transformation, the first two components in our output are the exact same as the two components in our input. So if these are both 0, that means x and y are equal to 0. Then x equals y equals 0. So this can only be the zero vector, which means the kernel of T is the zero subspace. Actually, since we know we're talking about a specific vector space, I should make my zero vector look like the zero vector in R2, right? So thus T is one-to-one. All right, now it says let's find an inverse function. Well, remember, the purpose of an inverse function is to take outputs and send them back to their original inputs. And again, the inverse transformation is not going to be defined with R3 as its domain. It's just going to use the range of this linear transformation. That's important because that tells me what these vectors here should look like. So I'm going to say let x, y, and I'm not going to call that z because this third component depends on the x and y. Specifically, it's x minus y. Let this be some vector in the range of T, right? Then we define T inverse from the range of T into our domain, which was R2, by T inverse. Now it should take this as an input because remember the range of T is now being treated as the domain of T inverse. Then the T inverse of this, what should this send this vector to? Well, should send it to xy because again, if I reverse the order, if I took T of xy, I want it to get me to this vector in R3, which we know that it will, just from the definition, okay? So it's fairly straightforward. It's using the original definition and just kind of putting the transformation on the other side, if you want to think of it that way. Okay, moving along. We talked a little bit about inverse transformations, and we've been using compositions in the definition of an inverse transformation, but we want to talk about some important properties of compositions of linear transformations. So let's suppose I have two linear transformations, T1 and T2, and T1 is going to map U into V, T2 is going to map V into W. Notice the codomain of T1 is showing up as the domain of T2. Then we call the composition of T2 with T1 the function T2. I use this circle here. Your book actually says to call this T2 circle T1. I don't like that notation. I'm just going to call it the composition of T2 with T1. Notice it would map U into W, and it's defined this way. It's defined the same way that you normally think of compositions of functions, T2 of T1 of U. Now notice this part makes sense, the domain and the codomain of our composition, because if you plug some vector U into T1, it's going to take you from U to a vector in V, and then that is also the domain of T2, so when that gets plugged into T2, it's taking you from V into W. That's where we end up. All right? So the first really important theorem here is that if T1 and T2 are linear transformations, then their composition is also a linear transformation. It's easy to show this, but you may just automatically assume that this would be the case, and it doesn't. You shouldn't automatically assume that. Yes, the composition is a function, but how do we know that that specific function also turns out to be a linear transformation just because these two are? Well, we're going to show that. Remember, what it means for a function to be a linear transformation is that it has to have both the additive and homogeneity properties. So let's look at the additive property first. T2 composed with, or the composition of T2 with T1 of the vector U plus V. Now notice U and V would both have to belong to the vector space U because that's the domain of this composition, right? So what does this literally mean? Well, this means T2 of T1 of U plus V. Now, starting in here, T1 of U plus V, because T1 is a linear transformation, by itself, it has the additive property. So I can split this into T1 of U plus T1 of V. That's totally fine. Now, think about what T1 of U and T1 of V are. These, individually, are the images of U and V. So plugging each of these separately into T1 produces a vector in V. So this is a vector in V plus another vector in V. And I'm plugging the sum of those two vectors into my linear transformation T2. Well, again, T2 is a linear transformation, so it also has that additive property, which allows me to split this sum of vectors into T2 of T1 of U plus T2 of T1 of U. And each of these, by definition, this should be a V. Let me change that. Each of these is the composition of T2 with T1 of the vector U or the vector V. So notice this split into that sum that we were looking for, giving us our additive property. Homogeneity is very similar. It's nothing complicated to prove, very straightforward, so I'll skip a detailed explanation of that. But we have from these two properties here that T2 of T1 is linear. It's a linear transformation. Okay? So let's work with the composition in an example. Suppose T1 is a linear transformation mapping M22 into P3, defined this way. So this is similar to one that we dealt with where we showed that the linear transformation mapping M22 into R4 was both one-to-one and onto at the beginning of this section. It's essentially the same linear combination, except instead of working with the ordered 4 tuple ABCD, I'm working with the cubic polynomial ax cubed plus bx squared plus cx plus d. But this is also a linear transformation, very easy to show that. And then I'm going to use a second linear transformation. And remember, if I want to do a composition of T2 with T1, then the codomain of T1 should be the same as the domain of T2. So P3 is showing up here again. This maps P3 into P2, and this is the derivative transformation. Remember, T2 of P of x equals P prime of x. We show that this is a linear transformation on the space of all continuously differentiable functions. So what we want is a formula for the composition of these two linear transformations. It's easy to do because if you think about what this means, we want to take something from our domain, T2 of T1 of, now the domain is the set of all 2x2 matrices. So I pick some arbitrary 2x2 matrix. When I plug that into T1, it produces the cubic polynomial ax cubed plus bx squared plus cx plus d. And then, when this gets plugged into T2, T2 takes the derivative of this. So this should be equal to 3ax squared plus 2bx plus c. This is the formula that we want. So rather than go through this in two steps, I can immediately go from here to here. If I plug in a 2x2 matrix, A, B, C, D, then A, B, and C are just going to show up here, 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 and here in this formula. Okay, so that consolidates everything down to just one formula. Here's another one. Your book states this as an example. I'm just merely stating it as an observation, but it's an important one. So if T is a linear operator, remember that means that the domain and codomain are the same vector space. And if I is the identity operator on that vector space V, then if you compose this linear operator with the identity operator in either direction, so T composed with I or I composed with T, either way you look at it, it's the same thing as just the linear operator T by itself. So I is acting like an identity matrix here, where it doesn't change the other linear operator that's being used. And you can see from this argument why that's the case. All right, we have one last theorem to prove here. Your book proves both of these A and B. I'm just going to prove B just for the sake of keeping this concise, but the proof of A is not anything complicated or outside the box, really. So you're welcome to look at that in your book. We're going to assume here that T1 and T2 are linear combinations. T1 from maps U into V, T2 maps V into W. This allows me to take the composition of T2 with T1. And we're also going to assume that they're both one-to-one linear transformations. Remember, that assumption allows us to use the fact that both of these have inverses. And that's kind of where we're going with this. If both linear transformations are one-to-one, then the composition, it turns out, will also be one-to-one. And that, remember, that implies that this has an inverse. Not only does it have an inverse, but I'm missing the -1 right here. Its inverse has a nice convenient form. Compare this to the inverse of a product of matrices. If I have the inverse of two invertible matrices A and B, so if I do A, B, and I want its inverse, that's equal to B inverse times A inverse. You reverse the order and then take their inverses. Same thing happens with compositions. So I'm not going to prove that it's one-to-one, like I said, but I will prove the second part, that the inverse of this composition looks the way that it does. My proof is much more concise than what the book does, but it works just as well. So what I'm going to say is, let's let W be any vector in the range of the composition of T2 with T1. Remember, the range of this linear transformation should act as the domain of this linear transformation here. Okay. Now, how do I show that this T1 inverse composed with T2 inverse is the inverse of the original composition in this order? Well, if we go to the definition of what an inverse is, if I do this function composed with this function, I should get the identity. In other words, I should get the original input that I started with, W. Okay, so I'm going to do that. Now, technically, we're supposed to show that the composition does this in both directions, but one direction is going to look almost identical to the other, so I'm only going to worry about one direction here. Take the original transformation, T2 composed with T1, and compose that with this guy right here, the inverse of T1 composed with the inverse of T2. What is this thing? Well, remember, in order to deal with a composition of two functions, I plug my input into this first function that produces an output, which is then plugged into the second function. But the first and second functions are themselves compositions of functions. So another way of saying that is that this big thing right here is the same thing as T2 of T1 inverse of T2 inverse of W. It's like this nested composition of functions here. Now, T2 inverse of W, remember, that's gonna give us something that's going to be used as an input for T1 inverse. But right after plugging it into T1 inverse, I do T1. These two things, by definition, are supposed to cancel themselves out. So I'm going to lose these two linear transformations, and then this T2 inverse of W is going to act as the input for this final transformation on the outside, T2 of T2 inverse of W. Again, because these are inverses, they, in a sense, cancel each other out, leaving me with W. So that means that this composition is the identity transformation, which means we're halfway there to showing that this is the inverse of T2 composed with T1. If I wanted to finish this, I would have to go the other direction and show that if I do the composition in the other order, switch these two here, that I also get the identity transformation, but the proof looks basically the same as this. So we just state that this way. Similarly, we can show that reversing the order does the same thing. Then that means that this thing is, in fact, the inverse that we said it was. Okay, so that's going to wrap it up for 8.2.